Welcome to Lecture 25. We begin something new today. We've been considering life in its past as it was thought about in the 19th century, and it was a fascinating topic, to be sure. We surveyed the whole century from the beginning of the era when the new science of biology was born, right on down to the creation of a theory of evolution by natural selection, with all that held for 19th century society. Along the way, we saw how important it was for explorers to get out into the world and see the wonderful diversity of life that it held. And we certainly encountered how the development of ideas about life in its past impacted Western humankind's conception of itself and its place in the world. With today's subject, we enter into our final series of lectures in this course. From here on, we'll be examining the theme of physical science and culture in the 19th century. So let's begin with a brief survey of what we'll be doing in these last 12 lectures. As has been the case throughout the course, we're going to have to be selective about what to include and what to exclude, and to emphasize, what to merely mention. I said way back at the beginning of the course that you'd be saddled with my choices of the subject matter. There isn't any prescribed or standard way to arrange the material from this period of the history of science, or from any other period for that matter. The history of science is so rich a subject that anyone bold enough to try to survey it has to pick and choose. And those choices not only deal with what specific scientific issues to include or to omit, they also have to do with the setting, the context in which science is pursued. Now, I've tried so far to sample from both the scientific ideas and their cultural context. Some people feel that past scientific theories that were later discarded carry no interest for us in the present. As you can tell from previous lectures, I don't agree. I believe firmly that you can't shy away from scientific ideas themselves, even when they challenge us. The reason we have to follow past natural philosophers through their solutions of technical problems is that there's simply no other way we can appreciate their achievement. We learn a great deal this way, of course. We learn about their creativity, but we learn more than just that. We learn about the process of theory construction in natural science in general. And that's a lesson we can carry beyond any given time or place, because we'll always be faced with the prospect of constructing a way to understand some new aspect of nature that has presented itself. Something similar can be said about our exploration of the cultural context in which science is pursued. We learn about the kinds of factors that have driven scientists. We learn about the social factors that have constrained scientists. We learn about the institutional forces that mediate natural science to the larger world and promote its interests in the public sphere. We learn about what's interesting to a given society and why. We learn what kinds of answers have credibility and what do not. And all of these factors continue to affect natural science. Modern scientists aren't immune to them. So we do, in fact, have a lot to gain by casting our net widely. The specific themes I've chosen in this last series are the ones that I find most compelling. As in the other two segments of the course, many of the topics chosen have a bearing on the question of worldview, particularly as it has been affected by new insights of physical science. The physical sciences we'll be considering, incidentally, include physics, chemistry, and astronomy. Let me remind you again that we'll be backing up in time from where we left off in the last lecture. We got to the end of the 19th century in our consideration of life in its past. We'll start at the beginning of the 19th century and proceed as we have up to this point. That is, we'll be guided by the subject matter of the individual topic we're considering. That might occasionally require us to back up in order to cover background material for the subject. Our first three lectures will be concerned with discoveries about new forces of nature and how they gave rise to new ideas about force itself. As we've learned already, the end of the 18th century was a fruitful time for the exploration of new forces of nature, especially electrical, chemical, and organic. This proliferation of different kinds of forces prompted the question about the nature of force in general. We'll look at the ideas about force that were inherited from earlier times. In particular, we'll examine the question of motive force. That's the force something can exert because it's in motion. There was a rich tradition about this question that went back to the 17th century, and we'll want to review it briefly. The reason why we need to examine the heritage of motive force is because it's from here that 19th century ideas about energy derive. Developments from the end of the 18th century and the beginning of the 19th century gave rise to another inquiry that had made its appearance at that time. I'm thinking here about the discovery of the way many forces were interrelated. These relationships of one kind of force to another raised an obvious question. Were all these individual forces manifestations of a fundamental force? That raised the possibility that one force could be converted into another. If there was a fundamental force, what could it be? Were chemical forces the basic forces? Now, this age didn't solve that problem once and for all, but it did make great headway on it, and it bequeathed the question to the scientists who came later in the 20th century. There it continued to motivate theoretical physicists, and they've passed this question along to the 21st century. With our so-called dreams of a final theory in contemporary physics, we're still fascinated with this prospect. Can we unite all of nature's forces somehow? Theoretical physicists today seek to unify what are now seen as nature's four fundamental forces into one set of equations. In our explorations of the 19th century, we're going to meet an early version of this very old concern with the unification of forces. And in the course of doing this, we'll follow the story of energy. We'll see that the ideas about energy, which are so fundamental to modern science, were not so much discovered as they were the result of a gradual emergence of consensus. We'll note how these ideas served as harbingers of a new understanding of the history of the world that required either adjustment of old religious notions or surrender to a secularized vision of the future. Along the way, we're going to learn about the creation of new institutions of natural science that begin to resemble those of our own day. Here's where we'll finally encounter the emergence of the scientist. I've been careful not to use that word until there was a practitioner of natural science who was recognized as such in the society. Well, that occurred as natural science became a profession. We've already had occasion to see how natural science really came into public view in the 1830s and 1840s, presenting issues and forcing choices for people who were not themselves involved with science. We'll see more of why that happened as we examine these new institutions of natural science. Following that, we'll be occupied with two major controversies, one about the materialism natural science allegedly demanded, and another involving the issue of extraterrestrial life. After we look at the materialism issue, we'll look at the way theories of the atom had matured around the middle of the century into a mechanical analysis of molecules that seemed to confirm the claims of the materialists. We'll note the impressive successes that became possible when scientists took the idea of a molecule very seriously. So seriously that they invested even detailed aspects of it with reality. Here we'll meet for the first time the question of the role of hypothetical entities in natural science. For the second controversy, we'll review developments in astronomy that helped to make the issue of life elsewhere in the universe particularly pointed. These involve national rivalries, a subject we've encountered already, and the attempt to test empirically with the help of new powerful telescopes the so-called nebular hypothesis that many found threatening. And then, when we come to the question of extraterrestrial life itself, we'll see that it challenged the 19th century to think the impossible. But what the impossible was may surprise you. Finally, we'll follow James Maxwell's ideas about the ether and their implications for the understanding of light and for the nature of scientific theory itself. We'll examine experiments that were meant to decide a fundamental question about light, and we'll learn that they were more confusing than informative. This will raise again the fascinating question about the status of hypothetical entities in natural science. How are we to understand them? Are they merely tools, or do they claim to represent the real world? Is their success in predicting outcomes sufficient proof of their actual reality? To end the course, we'll take stock of where scientists were as the century was coming to a close. Here we'll encounter the question about whether there is an end to science. This question was raised at the end of the 19th century, and interestingly, at the end of the 20th century as well. Is this concern something that emerges when an age is taking stock, as it invariably does at the end of centuries? We'll see what the lesson was for those who lived at the end of the 19th century, and then you'll have to decide for yourself whether the same lesson also applies to those who have more recently proclaimed that science is nearing its end. Now, with that overview of what lies ahead, let's begin our investigation of today's subject, the question about nature's forces and their interrelationships. I mentioned that there was a rich heritage of thought about the idea of force that we needed to review. It goes back, in fact, to the 17th century. If you've persisted this far in the course, you won't be shocked to learn that the problem about force I want to examine emerged out of the context of a problem we've met before, several times, in fact. I'm referring to the old theological problem of God's relation to the cosmos. Nor will you be surprised to hear me bring up again the name of René Descartes. I say you won't be surprised because we've gotten used to realizing that so many of the problems in natural philosophy we've encountered up to now have arisen out of concerns about worldview. This one's no exception. Well, this time the question had to do with God's attributes. Theologians and natural philosophers had given a lot of attention to the question of God's attributes prior to the 17th century. Historians of science, in fact, have argued that depending on what you said about this, you preferred one kind of natural philosophy to another. Let me explain. Say you emphasized God's omnipotence. God has all power. You might well assume that God could exercise that power as God saw fit. And that might mean that God could use it one way at one time and another at a different time. God could make up his mind differently how he would use and exert his power. God could, in effect, change his mind from one time to another. But suppose you emphasized God's omniscience. Because God knew everything, God didn't have to change his mind. That's why you could count on God's decrees. It was a question of understanding the implications of the decrees, which did not change. Now, I think you can see that if you emphasize God's decrees and God's immutability, then understanding nature was a matter of coming up with an explanation that was consistent with God's decrees. It was essentially an intellectual exercise that consisted of the creation of a system that was consistent with sound doctrine. But if you emphasized God's omnipotence and his right to change his mind, then you might be motivated to watch for differences and to explain things, especially to the natural world, or especially explain the natural world, on the basis of what you could confirm. You'd be more empirically oriented than those who emphasized God's immutability. Well, Descartes was one of those who emphasized God's omniscience. On the question about whether God would change his mind, Descartes was clear. God would not change his mind. God was immutable. What he said once and for all. And what he did once and for all. And this view had important and immediate implications for a fundamental question about nature. In his book, Principles of Philosophy, Descartes asserted that because God was unchangeable, and these are his words, He conserves the world in the same action with which he created it. Now, we need to pay attention to the word action here. What did Descartes mean by it? We're going to find that what this means in a second, but first I want to emphasize that with this idea of action, Descartes gave to natural philosophy a problem that would take a long time to solve. By the same token, the problem he raised here would contain dividends that were rich, far beyond anyone's imagination in the 17th century. Here's the problem Descartes uncovered. If all the individual actions in the world always add up to the same total, how are we to think about these individual actions? In considering this question, Descartes did what Schelling and those we've called romantic natural philosophers refused to do. He imagined himself stepping outside the universe and looking at it as if he were an outsider. He envisioned the universe as he imagined God saw it from outside. And what did he see? He saw a realm filled with material objects in motion. He saw the planets, of course, as they circled the sun, but he saw more than that. He saw all the motions of things on the earth, the horse pulling a cart, or one thing pushing against another. And it was all these motions, with their many collisions and impacts of matter, that constituted the world's action or activity. So we're beginning to get a handle on what Descartes thought this thing called action was. Now we know that Descartes was a mechanist, that is, he regarded the physical world as a gigantic machinery. From his statement above, the one about God conserving the world in the same action with which he created it, it's clear that Descartes felt that the machinery of the universe would not run down. Why? Because in spite of individual exchanges of motion, God made sure that no motion was lost. So the sum total of all the activity always remained the same. Descartes noted that God had given to individual motions of matter the property, as he put it, of passing from one to the other according to their different encounters. Okay, we have a general idea of what Descartes meant by action, and we know he felt that God conserved this action in the universe. But what about these individual actions, the ones that add up to give us the total? How did he deal with those? What did he mean by the property of motion passing from one object to another according to their different encounters? Well, Descartes identified what he called the quantity of motion of a given piece of matter. He reasoned that it depended on two factors: how big the matter was and how fast it was moving. So he concluded that the force due to this quantity of motion could be expressed as the product of the mass and velocity, mv. Now this is quite helpful, especially as we envision the universe, as Descartes did, as a continual collision between pieces of matter in motion. In a collision, Descartes said, whatever velocity was given up by one piece of matter was given to the other one, so that the total sum of the masses times their velocities remained the same. That's what he meant by the property of passing motion from one object to another according to their different encounters. And that's why the universe would run on forever, since no motion was ever lost. Descartes felt that mass times velocity, mv, was a measure of motive force. That is to say, the force a body could exert by virtue of its being in motion. I think you can see that his idea of action is bound up with this particular kind of force called motive force. And that makes motive force, sometimes also called mechanical force, a very important force in the cosmos. Why? Well, because getting matter to move is what's necessary for anything to happen. Without matter in motion, there isn't much to talk about. There's no activity, no life, no history, nothing. So motive force is a key force for us to consider. Well, problems soon arose with Descartes' approach, and they resulted in adjustments to his scheme. What happens, for example, if two equal blobs of clay move directly toward each other at equal velocities? When they collide, they don't pass their motion from one to the other. If you have two elastic bodies moving at the same velocities and they collide with each other, they do exchange velocities. That makes them rebound. They go in opposite directions at the same speed they were going before. Each receives the velocity the other had. That's consistent with what Descartes said. But that's not what you have when you have two blobs of clay. They stick together. And the motion, as well as the motive force, is lost. And if it's lost, then it would appear that the total sum of motion or motive force in the cosmos has been diminished. This is because the velocities, being opposite in sign, cancel each other. In fact, our old friend Gottfried Leibniz, whom we met back in Lecture 2, published a critique of Descartes' view in 1686. It was not that he disagreed with Descartes about God. He agreed that God's immutability meant that no motion would be lost. But he thought Descartes had gotten into the problem with the clay because he had the wrong idea of how to measure the force of motion. So he proposed a different measure of the quantity of motion and motive force. It was not, Leibniz said, mass times velocity, mv. That's not what was conserved by God. It was mass times velocity squared, mv squared, something Leibniz called vis viva. So vis viva, literally living force, was the name given by Leibniz to the quantity mv squared, his alternative measure of the force of motion to Descartes' mv. Now, mv squared had different implications from Descartes' mv. For example, mv squared was always a positive quantity, since the v squared. That meant that the mv squared of one body could never be canceled by that of another. But then what happens to the mv squares of the two blobs of clay we imagined colliding? There, said Leibniz, you have to move your attention away from the blobs of clay to the particles that make them up. The total quantity of motion represented before the collision is redistributed among these internal parts of the clay. The motion of the blobs before they collided does in fact stop when they collide, but that motion is nevertheless passed along. How? Well, said Leibniz, it's passed to the internal parts of the clay. It becomes the increased motion of the internal parts of each blob. So it wasn't lost after all. And the total original amount of mv squared that God had invested in the universe remained the same. In that sense, at least, the universe was not running down. Now, Leibniz didn't convince everyone right away, but for those he did convince, his vis viva shifted the focus of the issue. Leibniz was thinking of a different kind of measure of motive force. His focus was on the effect the moving object produced, not just the force, the push or pull that it exerted. And this difference between the force, the push a moving object exerted, and the effect the moving object had would become a crucial distinction in later physics. Let me illustrate this business of effect a bit more, and I can do it the way it was done right after Leibniz himself died. One of the followers of Newton in Holland did a series of experiments in which he dropped masses onto clay and measured the dents they made. You can see here that he was interested in the effect the moving object produced. And he found something interesting. Take two objects, same size, same shape. Now, although these objects look exactly alike in size and shape, suppose one of them weighs half of what the other does. Now, we drop them both onto the clay and compare the dents they make. What this Dutchman found was that they didn't make the same dent. That was to be expected. But you could get the same dent if you drop the lighter one from a point twice as high as the heavier one. Now, here comes the interesting thing. If it was dropped from twice the height, it wouldn't be going twice as fast when it hit the clay. It would be going faster than that because it was accelerating. You can calculate that it would be going 4 times as fast. The size of the dent, in other words, was proportional to the square of the velocity. So the effect produced was proportional to Leibniz's mv squared. Leibniz's measure of the force of motion did measure the effect a moving body produced. Now, in spite of this experiment, natural philosophers continued to disagree and to argue about the precise measure of the motion and motive force that God would not permit to erode away. By the late 18th century, natural philosophers were also exploring motive force in other contexts that were different from the collisions we've been considering and different from subjecting objects to gravitational pull. Nature caused matter to move, nature produced motive force in other ways as well. How? Well, for example, clearly heat could move matter. That was everywhere evident in the steam engines that had revolutionized industrial production in the 18th century. So heat could exert force on matter and make it move. Now, heat, in fact, will become a very special source of motive force to natural philosophers in the 19th century. It was so special, in fact, that we'll give it our full attention in later lectures. But heat is not alone here. Electricity and magnetism could also exert a force that caused motion in matter. Everyone knew that if you had two objects that were electrified similarly, they pushed each other apart. And of course, oppositely charged matter was pulled together by electrical force. In Lecture 12, we saw how galvanism could produce motion, that is, contraction, in muscles. And magnetic force also could be used to move pieces of iron by either an attractive or a repulsive force, depending on which pole of the magnet was used. And what about electrical current? Once Volta had invented his battery, a whole new field of electrochemistry was opened up. Electrical current was used almost immediately to dissociate water into its two gaseous components, hydrogen and oxygen. Here was an example of electrical force producing chemical change. So now we're not just concerned about transforming electrical or chemical force into motive force, we're involved with transforming one of these more exotic forces of nature into another one. The Englishman Humphrey Davy concluded it was misleading to say, as Volta had, that contact between two metals produced electrical force. Davy maintained that it was a chemical reaction that generated the current. This asserted an intimate and direct connection between electrical and chemical force. Chemical force became electrical force. And it kept going like that. Light became the subject of renewed interest around this time as well. In 1800, for example, the German-born British astronomer William Herschel stumbled onto something quite unexpected during an experiment in which he was exploring the relationship between light and heat. Here's what he was doing. He passed light through a prism to get the different colors of light. Then he measured how hot each different color of light was. While doing this, he noticed something odd. If he placed his thermometer in the region just below the red end of the spectrum, it registered the hottest temperature of all. What was going on here? Here was a region of what? Light? It was light that could be felt but not seen. Was it really light then? It was below the red light, which was the last visible colored light on that end of the spectrum. Then a year later, one of our romantic German nature philosophers discovered something about the other end of the spectrum of colored light. This was Johann Ritter, who was inspired by Herschel's discovery of infrared light. Ritter looked at things differently, as did most of those romantic natural philosophers. He was exploring something he called chemical polarity in light. He meant by that strange phrase that light was, in his view, the result of a balance among chemical forces, in the style of German nature philosophy, which, as we remember, could be very abstruse and philosophical. He explained that in white light, the two forces existed ineinander, in each other. The prism separated the forces to a state of being nebeneinander, alongside each other. So what did this outlook prompt him to do? Well, he didn't measure the temperature of individual colors of light. He exposed a chemical, silver chloride, to individual colors of light. And he found that the silver chloride was darkened to a decreasing degree as he went from violet on one end toward green in the middle, where there was no effect. As he proceeded on to red, he found that red light prevented darkening. So Ritter asked himself if there was a polar opposite of Herschel's infrared light, and quickly confirmed that in the region just above the violet end, there were what he called invisible rays that darkened the muriate of silver even more than did violet light. Ultraviolet light was for him the polar opposite of infrared. I think you can see that this was a time of fertile ideas. Now, these many connections among forces raised the question about how they might all be interrelated. Electrical current was always accompanied by heat, sometimes light when the wire glowed. Heat and light were intimately related, as Herschel had demonstrated, and light and chemical force were related, as Ritter showed. Electricity and chemistry were interrelated, as Davy persuasively argued, and most of these forces could also be used to produce motive force to move matter in one way or another. So it was almost natural to inquire if they could all be related to each other. Might there be one fundamental force of which all these individual forces were mere forms? In the next 2 lectures, we'll see examples of how these questions produced new and very important results.